Okay, let's go ahead and get started on topic 3.2, part 2. So just a reminder, so it says in the coordinate plane, an angle is in standard position when the vertex is at the origin. One ray of the angle lies on the positive x-axis. The terminal ray is the second ray of an angle in standard position. So what that means for us is this. I have one ray that is on the positive side of the x-axis. That would be the initial side. And the other ray will be somewhere in my graph on one of the quadrants or one of the x or y axis. And so the measure between your initial and your terminal side, so what they're showing there, that is the angle measure that we are referring to. So in this case, we're calling that theta. Okay, so the first thing you have to know is which way do we open for positive and negative angles. So in the box there it says positive and negative angles measures simply indicate the direction of the rotation. So 3 o'clock on our normal clock, standard clock, is going to be 0. That's where we start at because of the positive x-axis. And so what happens is if you are opening to a positive angle, you are going to go counterclockwise, which is what we did in our example. If you have a negative angle, you start at 3 o'clock, your initial side, and then you're going to open in a clockwise direction. So what we have here is an example of a positive angle versus a negative angle in terms of which way it opens. Okay, so notice that you can have a positive and negative angle that share the same initial side and that share the same terminal side as well. So keep that in mind as also as we keep moving through here. So it says, since we are using the coordinate plane to define angles, we can consider angles to have periodic behavior, meaning it's going to repeat itself over and over and over again. Kind of like tides, kind of like sun, kind of like temperature, things like that as the day goes on. It's going to just kind of repeat itself over and over and over again. Angles in standard position that share a terminal ray differ by an integer number of revolutions. So what that means is this. If I spin around, so if you think about a clock, so let me give an analogy. If you think about a clock and you think that it's at 1 o'clock, okay, what happens is I can spin the minutes around and around and around. Eventually, I can get it to reset back to 1 o'clock again. So based on that, there is a set number of revolutions where I can get it to land in the same location after I spin it multiple times. Okay, an angle theta is in standard position if the vertex is at the origin, its initial side, a positive x-axis, and so angle in standard position is said to lie in the quadrant which the terminal side lies. So what that means is this: for all of my angles, my initial side will be on the positive x-axis. If my terminal side goes like this, I'm in quadrant number 1, and I'm referring to this angle right there. Or I could put my terminal side in quadrant number 2, and I would be referring to this angle from my initial all the way to the terminal. I can put this in quadrant number 3, and based on my positive angle, it can go from the initial to the terminal. Or same thing with quadrant number 4. I can have something in quadrant number 4, and it's going to open all the way to that point right there. Okay, so that would be my 4 quadrants there. So example number 1, it says sketch the angle and determine the quadrant the angle is in. Okay, so what that means here is this. If I have 120 degrees, here is my graph. Okay, and so what's going to happen is 120 degrees is about 30 degrees past 90 degrees. So if I just draw something like that, 120 degrees opens positive. So that would be 120 degrees like that. So we are referring to this angle right there, so you can kind of see it easier. That would be what 120 degrees looks like. And the quadrant is in quadrant number 2. For the negative 110 degrees, we are going to start in quadrant we're starting with the initial side, and I'm going to go in a clockwise direction. I have to go past 90 degrees. So 110 could be something like that. So another 20 degrees past it. And so that would be negative 110 degrees. Okay, 180 degrees. So for 180 degrees, that is just straight across. So that's just my straight angle. So here's 180 degrees. Because it's positive, it's opening in that direction. So I'm showing the arrow to indicate which way that my line, my angle opens up. And then negative 275 degrees. So I have negative 90, negative 180, negative 270, and so it's just a little bit past negative 270. So there's negative 275 degrees. Okay. Oh, I noticed that I forgot to put all my quadrants. So this one leaves me in quadrant number 1. Okay. This one is on the x-axis. And then this one is quadrant number 3, like that. Okay, so it says an angle in standard position having their terminal sides along the x or y axis are called quadrantal angles. Examples of quadrantal angles are 0 degrees, 90 degrees, 180, 270, 360. Okay, and then if I keep adding multiples of 90 or subtracting multiples of 90, negative 90 degrees, negative 180. Okay, those are all different examples. Okay, turning the page. So the idea of coterminal angles. So co meaning more than one, right? So more than one angles that terminate at the same location. So two angles that have the same initial side and the same terminal side, but different amounts of rotation. So how many times are you spinning around? So if you think about a basketball player who does a 360-degree dunk, that means they spun one time and they dunked the ball. If someone pulls off a 720-degree dunk, that just means that they still dunked it in the same location, except they spun 2 times instead of 1. So that would be the idea of what a coterminal is. So if your angle is greater than 360 degrees, you just subtract 360, multiples of 360, until it's between 0 to 360, if that's what you're trying to graph. If your angle is less than 0 degrees, so if you have a negative angle, keep adding multiples of 360, and then that'll help you determine where to graph. So example number 2, it says find the smallest positive measure coterminal with each angle. Identify the quadrant the angle is located. So for 470 degrees, so I refer to the previous example. If the angle is greater than 360, subtract 360 until it's between there. So what would happen here is this. I would take the 470 degrees and I would subtract 360 from it. So what happens here is I do 470 minus 360 and I get 110 degrees. So what that means is that these two angles are coterminal with each other. So when I graph it, I graph 110 degrees, but what happens is I go 360 degrees, I make it around 1 time, that's 1 full revolution, and then I go to where 110 is, and that's where my graph is. Okay, so that would be 470 degrees, and then it's located in quadrant number 2. So even though it spun around my graph, I'm still referring to the angle right there that I highlighted. Okay, so that's what we're talking about there. For negative 60 degrees, I'm going to add, so for, negative 60, I'm going to add 360 degrees. And so when I add it, that gives me 300 degrees. So what that tells me is this. If I'm going to graph negative 60 degrees, I'm just going to go down 60 degrees like that. So this would be my negative 60 degrees, which is located in quadrant number 4. It is coterminal with 300 degrees, which means if I just start and I open this way and I go 300 degrees, that means that I have the same terminal side and the same initial side. So we're talking about right there in blue. Okay, so negative 60 degrees is the same thing as opening up 300 degrees. It's just one opens clockwise and one opens counterclockwise as well. Okay, let's pause here. Let's have you do number example 2B and 2D. Okay, so pause, give it a try, see what you come up with. Okay, example B, 1500 degrees. So what that means is I need to subtract multiple rounds of 360. So in this case, if I take 360 and multiply it by 4, 1500 minus that should leave me with 60 degrees. Okay, so what happens here is this. What that means to tell me is this is the number of revolutions. So when I want to do 1500 degrees, I'm going to go one time through, that's 360. I'm going to do a second time through, that's 720. And then I do a third time through, 1080. I do a fourth time through. Okay, and then now I'm going to go 60 degrees to finish it off. So, like that. So that would be 1500 degrees, which is the same thing. It is coterminal with 60 degrees. So that is located in quadrant number 1. Okay, and then the last one is negative 120 degrees. So negative 123, if I add it to 360, that's going to give me 237 degrees. So if I just open positively, so 90, 180, 270 would be at the y-axis. So negative 123 degrees is coterminal with 120, negative 123 degrees is coterminal with 237 degrees. So it looks like that. And that leaves me in quadrant number 3. Okay, so that would be the idea of positive, negative angles and coterminal. So measuring angles, it says the way that we will measure angles throughout this course and in future courses is going to seem a bit strange. The measure of an angle indicated in the figure on the right is arc length divided by radius, radians. So this is a new term that we're going to be working with, the concept of radians. Okay, so what happens is the radian measure of an angle in standard position is going to be the ratio, so a fraction, the length of the arc, so think part of a circumference, centered at the origin, created by the angle, to the radius of the same circle. Okay, so arc length over radius. So just a reminder, circumference is given by 2 pi r. So we can find the arc length by considering a ratio of the circle's circumference. So example number 3 here, it says consider the angle theta created by the quarter circle of radius 4 above. Find the measure of theta in radians. So what I have here, first of all, is a quarter circle. So if I want to find the arc length of a quarter circle, the arc length would be 1/4 of the circumference. Right? Because it's a quarter circle, you want a quarter of the circumference. Now, in this case, I am trying to find the angle measure between those two values there. Okay? Now, notice that my radius goes from 0 to 4. So that means that my radius is going to be 4. So I can use that in order to find the circumference. So my arc length is going to be 1/4 times 2 pi r, which is 2 times pi times 4. So 1/4 of 8 pi leaves me with 2 pi. So that would be the arc length. So my ratio, theta, is going to be arc length divided by the radius. So I know that the arc length is going to be 2 pi, and I know the radius is going to be 4. So that means that theta, my angle measure, is going to be pi over 2. And so that's what I know there. Okay. What I'd like to point out and indicate to you also is that because it's on the x and the y axis, that's also the equivalent to 90 degrees because a horizontal and vertical axis are perpendicular to each other. Okay, so in any case, The ratio in this case is pi over 2. Example number 4, it says find the measure of the angle formed by a third of a circle with radius 3. So if I want to find a third of the circle with a radius of 3, the first thing I'm going to do is I'm going to do arc length. So my arc length is 1/3 times 2 pi r. So that's 6 pi times 1/3. What you'll notice is a third of 6 pi is still back to 2 pi again. Okay, and this time my radius is going to be 3. So my theta is going to be 2 pi over 3. Okay, so that would be my, oh, and it says also in a clockwise direction. So because it's in a clockwise direction, it's going to be going this way. So what that means is it cannot be positive in this case. So this one, it's going to be negative. So theta is going to be negative 2 pi over 3. Okay, so that would be my answer to example number 4. Okay, so what we're going to be talking now is this idea of degrees, and we're going to be talking about radians, because again, we're going to have to be able to go back and forth between them. So what we should know now at this point is the equivalent values. So 360 degrees, one time around the circle, is going to be the full circumference. So 2 pi r. So because we're talking about 2 pi r with a radius of 1, 360 degrees is the same thing as 2 pi radians. So what that means is if I want to turn 360 degrees, that's also the same thing as turning 2 pi radians. So what that means is half of 360 degrees is 180 degrees. Half of 2 pi is 1 pi. Okay? And so therefore 1 degree is the same thing as, pi over 180 radians. And 1 radian is the same thing as 180 over pi. Okay? 1 radian is approximately 57.3 degrees. You do not have to memorize that. That's just factual information for you guys. Okay, so what we want to be able to do is convert between degrees and radians. So if I want to go from a degree to a radian, I take the degree and I multiply by pi over 180. Okay, the way that you can think about that is this. Usually, in normal cases, radians have pi in the numerator. So therefore, if I want to go from degrees to radians, I got to find a way to put pi in the numerator. If I want to go from radians to degrees, usually there are no pi when we're talking about degrees. So in order to cancel the pi in the numerator from radians, you need a pi in the denominator. So that's why it's to help remember it, pi over 180 versus 180 over pi. You just have to know, are you trying to add it or get rid of it? Okay, so example number 5, convert each degree to radians, leave exact as multiples of pi. Convert each degree to radians, round it to the nearest thousandth, and then convert each radian to degrees, round your answers to the nearest degree. Okay, so let's take a look at example 5. 15 degrees. So I'm going to go from degree to radians. So I have 15 over 1 times pi over 180. At this point, you can reduce. So if I reduce, I can reduce by a factor of, let me grab a calculator to make sure we're doing this right. So if I take 180, I will check to see if it's a multiple. So 180 divided by 15, it is. So if I reduce by 15, 15 goes into 15 once, 15 goes into 180 12 times. So I'm left with pi over 12. And that would be my equivalent value. Okay. For letter C, convert degree to radians. So I want to go to the nearest thousandth. So I have 419 over 1 times pi over 180. So if I just take 419 times pi and then divide it by 180, So 419 pi is approximately 1,316. I take that answer and I divide it by 180. So it will leave me approximately 7.313 radians. Thousandths is 3 decimal spaces, so I'm going to stop there. Okay, and then last one, convert each radian measure to degrees. So I have pi over 6. So again, if I want to go to degrees, in order to get rid of pi, I need pi in the denominator. So 180 over pi. So the pi's will cancel. I'm left with 180 over 6. So that leaves me with 30 degrees. So that would be my answer there. Okay, let's pause here. Let's have you guys try B, D, and F. Find the answers in radians or degrees. Okay, let's see how we did on example 5. So the first one I'm looking at is 720 degrees. So I take the 720, and in order to convert it, I multiply it by pi over 180. Okay, so I'm looking here, and I'm going to reduce by a factor of 180. So 180 goes into 180 once. 180 goes into 724 times, so I'm left with 4 pi in the numerator. So this would be 4 pi radians. Okay. The key difference when we're talking about degrees and radians is the idea of using a degree symbol versus using the word radian. So I can write this over here. If there is no degree symbol, we're going to be operating as if it were radians. Okay, for the next one, I have 16.3. So I have 16.3 times pi over 180. So I'll do 16.3 pi, and then I'll take that answer and divide it by 180. So that's going to be approximately 0.284 radians. And then for my third one, I have 8 pi over 5. So again, if I'm going to go from radian to degree, in order to get rid of the pi in the numerator, you need a pi in the denominator. So these will cancel out. 5 goes into 5 one time. 5 goes into 180 36 times. So I have 36 times 8. So 36 times 8 leaves me with 288 degrees. Okay, so if there's a degree symbol, we're talking about degrees. Okay, turning the page. For each of the following, sketch a figure of the arc length described on the unit circle. Find the measure for the corresponding for the angle corresponding to the given arc length. Okay, so 1/6 of a circle in a counterclockwise direction. So if I were to take a circle, and I'll draw on the x and the y axis like this. 1/6 means I need to chop this circle up into 6 pieces. So 1/3, let me reset that. 1/3, oh, my ratios are a little off. So 2/3, 3/3, 4/3. There. So I chopped it into 6. What you'll notice is there's 1/6. Oh, let me redo that one. There's the 1/6. There's the 2/6. And here are 3. So what you'll notice is, if I just number them, maybe they're easier to see. 1, 2, 3, 4, 5, 6. Well, actually, I kind of cut it into 12. So let me try this again. Okay. There we go. Here's 1/3. Here's 2/3, 3, 4, 5, and 6. Okay, so I cut it. So let me make it easier to see also by getting rid of the x and the y axis. Well, I need this one here. So there. There's 1, 2, 3, 4, 5, 6. So when I'm talking about 1/6 in a counterclockwise direction, I'm going in this direction here. So I am referring to this piece right here. Okay, and so if I'm talking about theta, that's going to be 1/6 around the circle. So around the circle is 2 pi, because 2 pi r is the same thing as 2 times pi times 1, the radius of 1. So 2 pi over 6 is the same thing as pi over 3. So that would be my theta in radians, is pi over 3. Okay, 2 full revolutions in a clockwise direction. So if I'm going 2 full in a clockwise, there's 1. So that would be negative 2 pi. And then I'm going to go a second time right back there. So that's another negative 2 pi. So that's the equivalent of negative 4 pi. That would be theta. Okay, for letter C, 3/4 of a circle in a clockwise counterclockwise. So here is my circle. And if I'm going to go 3/4, so there's 1/4, 2/4, 3/4. So we are referring to this piece right there. Okay, and so therefore this is 3/4 of 2 pi. And so 3/4 of 2 pi would be 6 pi over 4, which is the same thing as 3 pi over 2. Okay, and then the last one is 7/8 of a circle. So if I took this circle, it's already quartered. So if I quarter it again, I cut it into eighths. So 7/8 would be 1, 2, 3, 4, 5, 6, 7. That would stop right there. So 7/8 of 2 pi would leave me with 14 pi over 8. And so if I reduce that correctly by a factor of 2, that leaves me with 7 pi over 4. Okay, so that's what we're looking for there. Okay, sine, cosine, and tangent. So now we're starting to put it more together. We talked about sine being vertical displacement over radius, cosine being the horizontal displacement over the radius. So what's going to happen is this. We're talking about this idea of a unit circle. A unit circle is a single unit where the radius is 1. So what that means is because sine was the vertical over the radius, if the radius is 1, it's just the vertical displacement. For my cosine, it was the horizontal displacement over the radius, but because the radius is 1, same thing. It's just the horizontal. That's why you have the x and the y. So again, if you use the x down on the bottom, on the x-axis, or on the top, it's fine. It creates the same thing. So whenever you're given an ordered pair, what you'll notice is the x-coordinate of the ordered pair matches up with cosine of theta. The y-coordinate of the ordered pair matches up with sine of theta. And then you have y over x, which is sine over cosine. Okay, so let's take a look at example number 7. So it says the figure shows a circle centered at the origin with an angle of measure theta in standard position. The terminal ray of the angle intersects the circle at point P. The coordinates of P are 1/2 square root of 3 over 2. Find the following values. So that means that this is the x-coordinate and this is the y-coordinate. So if I want sine of theta is just the x-coordinate. So sine of theta would be 1/2. Cosine of theta is going to be the, I'm sorry, I got that mixed up. Try that again. The y-coordinate is root 3 over 2. Cosine is the x. That would be 1/2. And tangent. So tangent is going to be y divided by x. So square root of 3 over 2 times 2 over 1. So notice that the 2's are going to cancel. You're just left with square root of 3. Okay. Let's pause here. Let's try to get you to do example number 8. So pause, try it out, see what you get, and then we will go ahead and get continue on to the very end. Okay, so for example 8, point R is the result after point P is reflected over the y-axis. So what that means is if it goes across the y-axis, it's going to end up here. So the x-coordinate is now negative. The y-coordinate is still the same. It doesn't change. So all we're doing is just using an opposite x value. So The y value is the same. That means sine is still root 3 over 2. The x-coordinate is negative, so that would be negative 1/2. And so if I do y divided by x, I have a positive divided by a negative, so that's just going to leave me with negative square root of 3. So I got negative root 3 over 2 divided by negative 1/2. And that's how I get my answer there. Okay, so last page. Unit circle is a circle centered around origin with a radius of 1. So what that means is we're going to have to be able to fill in this circle with angles and degrees. So because it has a radius of 1, that's not going to be at a full impact at the moment. So let's start off with 0 degrees. Okay, so 0 degrees is going to be there. Now, there's two multiples that everything is going to be based off of. It's going to be based off of 30, and it's going to be based off of 60. So for the 30 degrees, I'm just going to use this pink. Okay, so 30 degrees, 1, 2, 3, 4, 5, 6. Okay, everything in pink is a multiple of 30. So what that means is 30 degrees, 60 degrees, 90 degrees, 120, 150, 180, add another 30, add another 30, add another 30, 30, 30, and then 360. So that one's easy. Okay, I'm going to use the same pink for radians because we want their equivalent values. So these are all multiples of 30 degrees still. Okay, now 0 degrees is the same thing as 0 radians. 360 degrees means it's going to be 2 pi radians. Okay? A semicircle is half of that. So half of 360 was 180. That means half of 2 pi is going to be 1 pi. Now 30 degrees, notice that when we do this, we cut it into 6 pieces of pi. 1, 2, 3, 4, 5, 6. So because of that, that means that 30 degrees are 1/6 of it. So what that means is this is 1 pi over 6. This is going to be 2 pi over 6. But what I'm going to do is reduce it. That's pi over 3. This is 3 pi over 6. That's half of pi. This is 4 pi over 6. Again, I'm going to reduce it. 2 pi over 3. This is 5 pi over 6. This is 6 pi over 6. This is 7 pi over 6. 8 pi over 6, 9 pi over 6, 10 pi over 6, so this is 5 pi over 3, 11 pi over 6, and then this is 12 pi over 6, which is the same thing as 2 pi. Okay, the last one is going to be the 45 degrees. So these are all multiples of 45. Okay, so what that means now is because it's multiples of 45, this is 45 degrees, 90 degrees, 135, 180. I have 225, 270, 315, 360. So you just keep adding 45 degrees to that. For this one, when I do my 45 degree angles, what's going to happen is 1, 2, 3, 4. Now I am quartering this. So if you think about it, 1, 2, 3, 4. I'm cutting pi into quarters. That means that's all denominators of 4. So the first one, 45 degrees, is 1 pi over 4. The second one is 2 pi over 4, which reduces to pi over 3. This is 3 pi over 4. This is 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. So that's how we get our degrees and our radians. If you read through these hints, it kind of makes sense. I'm not so interested in the shortcuts. Even though you want to take a look at it, you can. Just know multiples of 30, multiples of 45, multiples of pi over 6, and multiples of pi over 4. And then you just reduce it down from there. These are the angles and degrees and radians that you're going to be given a speed test on. So understand where these numbers come from and then how to put them in the correct spot. Okay, that's it for 3.2. Stop it here and then turn it in tomorrow.